setup. Quiz 1 in a beach board. Okay, so go to a Dropbox and put your quiz 1. Okay. Now, what is a quiz 1 about? So quiz 1 tonight is just for you to put some, introductory paragraph, about yourselves. Very simply, maybe you might want to put some name down, your major, and class. What is it? Junior, sophomore. What is it? Sophomore or the senior status, and whether you're mechanical, civil, or aerospace, and maybe number of hours, per weekly basis, how much you're working. And if you work at the, what is it, in some engineering company, then you can probably say, hey, I'm working 20 hours per weekly basis at, the ABC companies, okay? And, and then maybe 4 would be, what is your short-term goal? Once I graduated, after this summer or a year later, I want to be working as a manufacturing engineer at this, XYZ company, blah, blah, blah. Or if you have some other aspirations, that would be good. Okay, some people wanted to go into the military, okay, become an officer. Some people wanted to continue on doing their, pick up the higher educational, what is it, degree and something like that. Okay. So, but before you do that, I want you to get a, scanning apps. Okay, there are some cheaper ones, and if you write this, handwritten all those, and take a picture and convert that into the PDF, not the PDF. What is it? The Adobe, right? File. Okay. And then load this up to a beachboard, okay, Dropbox, okay, as I have shown you about a minute or two ago, okay? And that will be your quiz for tonight. Okay?
Do you want just this as a bullet points, or did you just want full sentences, or what do you want?
Bullet points are fine. If you can put it in a sentence form, that'll be fine. In any form you can, but don't give me, entire essays or something. All right, just very brief. That'll be good. Okay.
What are 3 and 4?
Dr. Kim?
Yeah.
What did you want for number 3? Oh.
I'm sorry, go ahead.
What did you want for number 3 on the bullet list? I can't really read that.
The
Word.
Or if you have anything else that you want to share, that'd be good. Hey, my hobby is blah blah blah. I play for the collegiate, soccer team. That'd be good. Okay. Or anything that you want to introduce yourself. Okay. But don't put too much time into it. Okay. My objective is see if you can be able to convert this file into Adobe format and see if you can be able to punch those files into my Dropbox. Right. So this is
Professor,
exercise.
when is this due?
After this class over, so maybe you might want to be able to do it by next Wednesday before the class.
So professor,
Okay.
is the name, major, work, and what's number 4?
This is like your short-term goal. What do you want to be, after graduation? What do you want to do? I mean, to do after graduation. Okay. Hey, it doesn't really matter. I mean, if you switch it in this way or that way, I don't really care. Okay. And you don't
When
have.
you say Adobe, you just want the file on PDF?
Yeah.
Okay.
PDF, not the PDF. This is the word that I'm looking for.
Yeah, PDF.
Yes. Convert this file into the PDF and punch those in.
Because
Now,
I do have a notepad application that I
Yeah.
just write on it on my
Yep, that's it.
on my tablet, and it
Yep,
just
and-
uploads it onto PDF.
Yep, and then drop that in. That'll be
Okay,
good.
cool.
If you're in a Word format, I think I can be able to read Word. Okay, would be okay. Word or PDF, either one is fine. All right, let's go through this. Last time, we take a look at the position and the velocity and the accelerations and their relationships. The velocity is basically changing in position with respect to time. Acceleration is changing in the velocity, right, with respect to time. So first derivative of the position vector will give you velocity, and what is the first derivative of the velocity will give you an accelerations. Okay? So we look at the two different motions, right? The motion with a constant velocity, and the other one is a motion with a constant gravity or the accelerations, such as dropping the ball. Okay, so whenever somebody asks you, hey, what is your position, velocity, and acceleration at the time, then you're asking, or you are asked to find the kinematics, okay, of the dynamic problems. So we drop the ball at rest, and I asked you to find the position, velocity, and acceleration when this thing is passing by 11.28 meters. So this is initially at rest. That means velocity is 0. And I'm going to treat the x starts at this point. Let that be equal to 0. Acceleration here is something. So we wanted to find that. So x, we know, position is 11.28 because I asked you to find the velocity and acceleration when this guy passes through this point. And so we found that the time, I'm going to click the time starts at 0. So time here was 1.517 seconds. And the velocity was 14.69. What is it? The meter per second. Now the gravity is acting So in any point when the ball travels, the acceleration or gravity is pulling downward. So therefore, this is a constant or the uniformly accelerated motion. In this case, your acceleration is simply the gravity. A is g, which is 9.8 meter per second square. A in this case is 9.8 meter per second square. So this is a constant, and this gravity is applied from here to here. Okay. But however, the velocity is not constant. At the rest, the velocity is 0. When the ball passes or passing through the 11.28, the velocity was 14.869 meter per second. And I gave you some kind of a homework. Now my homework is not to be turned in, okay? And whether you do them or not, it's your own, make a decision. But if you prefer, if you can just go ahead and take a look at it. And also there are similar, the problems in the back. Plenty of them. Okay, just go ahead and choose and start working it. Okay. I'm not sure you have all the answers from the back of the textbook, but you can just go ahead and scan it through, and if you want, you can go ahead and attack the problem. The problems which you were given a solutions, so you can be able to check them. Okay. If you hit the wall, just go ahead and contact me and let me know. What you're up to, then I should be able to help you out. And if I see a lot of emails on this particular or similar problems, then I'm going to stop responding it, and I'm going to bring that into the classroom and we'll solve it. Okay. All right. And I told you to do this problem. Now, I'm here, I'm going to toss the ball upward, and that upward direction would be a 5 meter per second. And this ball will go up and reach the some ceiling point, and then it will be dropped down. Now this distance or height is 10 meters. And this is a position 1, this is a position 2. And I need you to find the time and the position, height, and the velocity and accelerations at position 1. And I need you to find the time and the position and the velocity and acceleration when the ball hits the 10 meter below where you started from. And I'm gonna start from here. So
Doctor, can you record it?
Say that again.
Can you start recording?
Let me see. I think this is the one. Oh.
Yeah, that's.
Yeah, it's recording on our side too.
Okay, good.
Thank you.
Okay. How do I get back? All right. So I'm gonna give a coordinates. I'm gonna start everything from here. Time equal to 0. So I'm gonna measure from the time equal to 0. And I'm gonna set the my starting point as x equal to 0. So upward direction is x positive. Okay, if the ball hits downward, then that's going to be negative directions. And the velocity is given 5. And let's go take a look at this position, or at this position, or at this position. Okay, follow the ball. Okay. At any locations, the gravity is acceleration is pulling downward. Okay. This acceleration applies to a gravity 9.8 meter per second. Now note that the your acceleration is in this direction, but your x is defined to be positive upward. So therefore, your acceleration is minus 9.8. Okay, does it make sense? So acceleration here is minus 9.8. Here, minus 9.8. Here, minus 9.8. Okay. Now, when the ball starting from this, and then it travels up and then it's gonna stop at here before it changes the velocity downward. In other words, from here to position 1, it slows down and then it's gonna drop. Okay, change position and then it's gonna drop. So what is the velocity at this location?
0.
Yep, that's a 0 right there. So that makes life a lot easier. So this is considered to be a constant or uniformly accelerated motion, which means it's the motion with a constant velocity. Constant acceleration. The governing equation for that is x is equal to x naught plus v naught t plus 1/2 times acceleration t squared. V is equal to v naught plus at. Acceleration is given as an acceleration. So in this case, this is going to be minus 9.8. Okay, so this applies the motion at any places from here to here. Now we are looking into at this location, position 1. Position 1, you said my velocity is equal to 0. The initial velocity was given 5. Plus my acceleration is minus 9.8 t. So time it takes, right, to get up to the highest point would be a minus 5 divided by minus 9.8. So they will give you 0.51 seconds. So this is 0.51 seconds. So from the initial point, getting up to the highest point, it will take about 0.51 seconds. Now, how high? Okay, now I'm going to put that into this equation. Wanted to find the position of this ball when at the time of 0.51 seconds. Now the x, let me rewrite this guy. So initial position, I put that as a 0 because I'm starting from right here. Plus initial velocity given was 5 plus 5 upward. Time was 0.51 seconds plus 1/2. Acceleration was minus 9.8. Time was 0.51 square. So let me see. Where my calculation go? Okay. It's up to 1.28 meters. So about what? 4.5 foot, okay, traveled. So this 1.28 meters. So that means that from here to here is the 1.28 meters. So everything is captured. Now coming down in this case. Now take a look at it here. This guy. We know where this ball is. That means we know its location. Can somebody tell me numerically where is this the position of the ball?
Negative 10 meters.
Exactly. So this is a positive, but this guy is at the negative 10 meters down. Okay, we know where that is. So let's go. I'm going to use this equation again. So x is equal to v naught. Well, let me just go ahead and say 5t plus 1/2 times minus 9.8 t squared. Okay. Now we know position for the ball. I mean, we know the ball position at P2 locations. That is minus 10. 5t plus 1/2 minus 9.8 t squared. So this is a quadratic equation. Okay, so I'm going to go 1/2 minus 9.8 t squared plus 5t. Move this guy over the other side and make this guy equal to 0. So this is going to be basically ax squared plus bx plus c. You just have to solve for the t. In this case, x represents the other t. So if you do that, and I have two roots. One of them is 2.027. The other one is minus 1.06. So don't take this because we don't define the negative time. Okay. So it will take 2.027 seconds when the ball starts from here. Starts from here, move up, and come down. And it took about 2.20 seconds. Okay, we know t, then we just have to compute the velocity. So the velocity was v naught plus at. Initial velocity was 5. Acceleration is 9.8 t. So substituting t equal to 2.027, your velocity is, I gotta compute that, minus 14.8646. Oof. I didn't have to go that far, but that's okay. So it's minus 14.8646 meter per second squared. Why minus? because your positive defined to be upward. So the velocity of this guy is it's actually going this way with a 14.8646. Okay. Now look at this guy for a minute. It's a little bit complicated, and maybe let me remove. Thing or two. Okay, it's gonna, okay, so I shoot the ball upward and then it slows down and stop at, stop at here. And then it start to change its motion, direction, and went down this way. Okay. So I can separate this point. So which means that this is acting as, I'm gonna hold this ball and at rest initially, and I let it go and let it travel down here by, this is a 10, this is 1.28. So this is going to be a distance of 11.28 meters. Okay, so I'm going to so this is the same thing as initially at rest. I'm going to release the ball initially at rest and travel down to a 11.28 meter much. And I want to know what kind of speed, accelerations, and time it takes to get there from position 1 and 2. So time difference would be 2.07 right here minus this guy, because I didn't set this as a reference 0, and that time would be 1.517 seconds. So it takes about a 1.517 seconds to get there from position 1 to position 2. Okay, so velocity at hits here would be a 14.46. Okay, so that is exactly what we did last time. The ball travels 11.28 meters. The velocity at the position 2 would be 14.869. It's a downward because in here I set the coordinate to be a positive downward, and it takes from here to here 1.51 seconds, and that's exactly what it's mimicking. 1.51 seconds and 14.86. All right, so they are related. Okay. This guy, I shoot it up there, and that's why what goes up and it will come down, right? And what happens if I shoot the ball in this direction? Oops, why is it not? What happens if I shoot the ball with an angle, with some kind of a velocity? And this guy will travel, and it will hit somewhere. So at any point the ball travels, the gravity is pulling. So when you look at it from this side, the ball is just going up and down. So up and down motion of this ball would be a constant, we treat that as a constantly accelerated or uniformly accelerated rectilinear motion. So we're going to use the equations like this for up and down, the vertical motion. But this guy, okay, unlike this one, just going up and down, this guy, I mean, moves this way, wide open from here to here. So it's got to have a velocity in the horizontal direction. And this is a constant gravity is pulling it down. And this one is a constant velocity. So the horizontal motion will be treated as a uniform the velocity rectilinear motion. Okay, so up and down, the vertical motion will be taken care of by assuming that the it's going to be constant acceleration. Motion with a constant acceleration. But horizontal motion, there is no accelerations, and however, we will let the velocity equal to constant. So velocity at here, 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 here would be same as the horizontal velocity. The vertical velocity, okay, or vertical motion will be associated with a constant acceleration. Okay. Let me see. Okay, now I have I shoot the ball into this direction with a velocity of 180 meter per second at about 30-degree angle. And this guy travels, go up, it's a projectile, and it hits the ground right here. And this distance would be 150 meters. Okay. And I'm going to define let me see. Okay, I'm going to define my x, my y in this direction. Let me see. Okay. So, so I wanted to find out what is x position. And what is y, the position. And what is the velocity in the x direction, the velocity in the y direction, and the acceleration in x direction, and acceleration in the y direction. Y is vertical motion, x is the horizontal motions. Okay? So we know y is at the minus 150 meters. We already know the position of the Y, which is 150 below that the cliff. Uh, mm, yeah, I forgot to set the triad, the coordinates. Whether I put it in here, put it in, I don't remember. I'm just going to have to go through this. Okay. Now the gravity or the acceleration is applied here as minus 9.8 meter per second squared. In the horizontal x direction motion, there is no accelerations. But that this guy, the velocity in x direction is constant. Okay, but we do not know how far it's going to travel to the right. Okay, so at this location, where I shoot the projectile with a velocity of 180 meter per second at the 30 degree. I'm going to find the velocity in x, initial one, the initial velocity in the y directions. So this guy would be 180 times cosine of 30. This guy would be 180 sine of 30. So this is a 90, I think. So that's going to be 90, and this is going to be 155.9 meter per second. Okay. All right. So the velocity here would be 155.9 meter per second. Okay. Now we just have to find the time it traveled and time it takes to get there. So these are the the parameters that we're going to work with. Okay. Now the vertical motion, the up and down, the y direction, y motions. Your velocity, I mean not the velocity, the y would be defined to be y plus, and the VOT plus 1/2 times acceleration t squared. But however, in order to distinguish between the initial velocity and the y from the initial velocity from x directions, and the velocity in the y would be depending on the initial y velocity plus acceleration t, and the acceleration in y is the gravity, which is 9.8. This is the g, meter per second squared. And the governing condition for the horizontal motion, this would be x direction motion. In x direction motion, same thing. X is equal to x naught plus VOXT. There is no accelerations. The VO, not the VO, the velocity in the x direction is just a constant. Same thing as the initial velocity in the x direction, which is 155.9 meter per second. So it makes a lot easier. So we know what this is, okay? And you can go from there. So since I put this guy into a starting point at the cliff, and I'm gonna let this guy equal to 0. And that makes life a little bit easier. Okay. Now at position, let's say this is a maybe, I'll call that as a maybe position 2 or position 1. I'll just, okay, so at point 2, now the y here would be a minus 150. We already put that as minus 150. And the velocity, initial velocity in y direction is 90. T plus 1/2 times acceleration is 9.8 t squared. Okay, so you can obtain the t here would be 19.91 seconds. So you still have to solve the what is it? Quadratic equations. So it takes 19.91 seconds from here to here. Okay. So in this case, the vertical motion at this formulation gives a information how long it takes to hit that the ball to hit the position 2, 19.91 seconds. Now you're going to use that information to find how far it traveled in the horizontal directions. We know how long it's going to go up and down, right? The ball to travel go up and go up here and then hit it down here. So that takes about 9.91. So we're going to use this information to find the how far it traveled, which is VOXT. And this is constant value, which is 155.9 meter per second times 19.91 seconds. And that guy will give you around 3,100 meter. So it traveled from here to here, 3,100 meters. Okay. Okay. Now, so we got the position, XY positions, the velocity of X. We still have to work this out. We know the accelerations, and we know the time. Okay, so let's go. We need to, so Vy is the velocity of the ball traveling in the vertical motions. So that's the one that I'm going to use. So velocity of the ball in the y direction is defined to be like this. So this guy was given as 90 plus minus 9.8. So the ball velocity when time was 19.91 seconds. So Vy I got was, let me see, where is it? Let me go find out. 90. I have minus 105.118 meter per second. 105.1. So this is going to be minus 105.1 seconds. So we have captured everything that we need here. Okay. So let's go take a look at it here. Okay. It starts from here with the velocity of a 180 at 30-degree angle. The projectile, it will travel and it will hit the ground, which is about a 150 below the cliff where I shoot the ball. So at this P2 location, we know from here what is the position X and Y, which is it traveled to the right 3,100 meters and 150 below the cliff. And the velocity here, or the horizontal velocity was 155.9 meter per second, and the vertical velocity was 105.1 in this manner. So this is X and Y. So the net velocity would be, and you can do the vector sum. So which is a 155.9 square plus 105.1 square, and you can be able to find the angle. Okay, and that angle doesn't always have to be 30 degrees. So you're gonna have to find that angle. So that is the final magnitude at position 2. And acceleration is the same. The acceleration here is 0, and the acceleration here is 9.8 downward. So the only acceleration is downward. Okay. Now, can you be able to find what is the maximum height that this guy? Okay, so I'm going to call it as a position 1. Find the time from the start it takes to get up to the highest position, and when does it happen? X and Y. What is the velocity at this at position 1? And what is the acceleration at the position 1? And I hope you can be able to fill that out. Okay. So in this case, your velocity going up and down in the y direction is 0, just like the we did this, right? Toss the ball up, stop, and it will come down. Same thing. It just went to the right, but it's the same up and down motion. Equation of motion governs it. Okay, and this is going to be minus 9.8. We don't have acceleration. This is going to be 155.9. Velocity is 0. Then you should be able to find time it reaches the maximum height and position. Okay. So so velocity of y is 0 at position. So you look at it over here, the vertical formulations. Okay. So y is equal to y0 plus by0t plus 1/2 times at squared. And this is going to be 0. Initial y velocity was 90 t plus 1/2 times minus 9.8 t squared. And okay. Oh, no, what am I doing? Gee, this would be a lot simpler one. Sorry, I carried away. So the velocity at y is equal to vy0 plus 9.8 t. So velocity at when the ball reaches the position 1, the maximum height, and this guy would be 9e plus minus 9.8 t. So you can be able to get the time. And that time is 90 minus 9.8. That should give you 9.1743 seconds. So it'll take the about 9.17. So it will take about 9.174 seconds to get there. Now you can easily find the x and y. Maybe I'll reuse this guy. So punch this guy in here and here. So I want to find the position when the time is 9.17 seconds. So once you plug those in, what I got is 413.2 meters. Okay, so 413. So this distance, the maximum height would be 413.2 meters. So that distance is the 413.2 meters. Now, what about here? That's easy right there. The horizontal direction, this is the governing equation. Okay, where are you to the right when time is 9.17 seconds? So maybe I'll write it here. So X position, excuse for the short memory, that's gonna be a X naught plus VOXT. This is set to 0. This was like 155.9 T. So when T is equal to 9.174 seconds, let me compute that. 155.9 times 9.174. So I have a 143.2 meter. So 1430. The position of that is a 1430. So at the 1430, 412, and that's the position of the ball when it hits the maximum height. It takes from here to here about 9.174. At this position, the velocity, horizontal velocity is 155.9. The velocity here is 0. The gravity is acting downward 9.8. There is no acceleration to the right. And that, we explained everything. Okay. So that's how you work that out. Okay. Now, again, we go back to position, and the velocity is dx dt. Acceleration is dv dt. Sometimes you can get the, you know, do something like this, where the kind of a dx's are canceling out. Now, this we know is a velocity. Okay. Now, this would be an acceleration. It can be written as a velocity times dv dx, not t, not the time. So if I were to shift this and changing the position, that I can write this one as a dx. And between 1 and 2, 1 and 2, or 0 and 1, it doesn't matter. So v2, this would be a v squared divided by 2 between 1 and 2, a x between 1 and 2. So this is going to be v22, v12, ax2, ax1. And the v2, I'm going to do this way. And I'm going to just go ahead and do this. And the v12 equal to plus 2a x2 minus x1. Right? So this would be the position at 2. This would be position at 1. And this is the position, and that's the position. So velocity at 2, velocity at 1 can be defined in this way. So you can use, instead of a v2 equal to v1 plus, the acceleration and time variations. Now you can go ahead and change the your velocity. The index. You can go ahead and say, hey, v final is equal to initial velocity plus 2a times x minus the x naught. So you can go ahead and do that. And some other text can be seen as finer with respect to x final, or some other can say v2 plus 2a simply delta x. Okay, so you can use it. So we all up to this far, you've been seeing the velocity with respect to the time variation, but in this case, velocity can be changes in velocity can be written as a displacement, but only difference would be the velocity square. So you need to be a little bit careful. Okay, what time is it? So this will probably end the lecture about the any motion in straight line. That's why it's called the rectilinear motion. Okay. But nothing ever moves a straight line, right? Most likely it will be curved. So we will be looking into a kinematics about when the particle moves, in a curve. So far we talked about the rectilinear, but now we're gonna look at the curvilinear motions. So let's say we give it some kind of reference frame, and the ball here is moving along the curve like this. So at time 1, we define the position x and y. Okay, so we know where that guy is. At time t2, position y and the velocity and acceleration. Obviously, we need to know that, everything. Okay, so position 1, and at time 2, that's position 2. So it travels in this manner. And that guy is, I'm going to call that as a delta r. I'm going to take the limit of delta r divided by time between this and this, and take the delta t goes to 0, and that is considered to be a velocity. So more physically defined, this is going to call the instantaneous velocity. Okay. Now, as delta r, this guy, this would be delta r. Now, if the time is shorter, okay, make the delta t smaller. So that means I'm going to bring the R2 into a lot closer to there. But look at the changing in the directions. So it will be more of in alignment to the tangent to the motions. Okay. So therefore, this velocity is very closer. In fact, it's going to be tangent to the motion. So velocity, if this guy moves, I don't care, here, here, or here at different time, the velocity is always and tangent to the path. Okay. All right. And the similar token, I'm going to approach the delta t equal to 0 with a delta v and delta t, and there will be defined a instantaneous acceleration when the ball travels in the curve. Okay. Now, acceleration, it doesn't have to be a tangent or collinear with the velocity vector. Okay, these are all vectors. Okay. Okay. The acceleration could be, I don't know, maybe here, or here. This could be an acceleration. Okay. So we have to kind of capture that. Well, when this guy travels in a straight line manner, here or here, the velocity will be always the same, and the acceleration would be, in the directions. If this guy slows down, then it could be opposite directions. Okay, but still the acceleration will be in a straight line. But in the curvilinear, it's everywhere. So you have to kind of compute that. That's all. It makes things a little bit difficult. Okay, now you can describe the motion in a what do you call those? In a normal XYZ coordinate system. Okay, but sometimes it might be easier to define kinematics in a different coordinates. So, oops. If the ball is traveling in this direction, and I'm gonna define that to be ET, and its normal is EN directions. And I'm gonna define the my kinematics depending on the tangential and normal coordinate system. Not through X and Y, it's through the ET, that's the unit vector, and EN. So this means tangential to normal. Tangential is the tangent to the curve, and 90 degree from the tangential direction, and your normal is defined in this way. Okay. Now we know the velocity is always in the tangential direction with some kind of a speed. This is a vector. This is a scalar. Okay, so this is a velocity. This is the speed. This is the direction. So velocity is a vector, has the magnitude plus the directions. Okay. Now we can define, once the velocity is defined, and the acceleration can be defined. Acceleration is simply dv dt. That's it. Now at this location, boy, your ET, so I'm going to call that this is a position 1. This would be a time 2, position 2. So the ET and the EN keep on changing. Okay, unless the I mean, if we were using just the X, Y, G, and that guy is fixed, okay, and it's the unit direction is IJK. That guy is fixed, but the tangential normal coordinate systems, and these two are kind of moving along the particle, traveling the curve. But as far as the mathematic is concerned, we'll just take the first derivative of it. So that's going to be a v dot et plus v et dot here. Okay. Okay. I'm going to integrate this guy with respect, derivative with respect to the first what is a quantity, and leave the other one as a constant, and then vice versa. Keep this as a constant, and I'm going to take the first derivative of the ET. That's what it is. And this, we know, this is the velocity change, changing in velocity with respect to time, the velocity with respect to, so this is acceleration. So this is acceleration in the tangential direction. That's a scalar acceleration, some kind of number in the ET direction. And boy, what is this? Now look at the ET1, ET2. I'm going to put that into a, so this is ET1 and that is ET2. And this difference here is delta ET. And I'm going to keep this as a d data. Okay. And this unit is 1. the length of that is 1 because that's how the unit vector is defined to be. Okay. Now I'm going to change limit delta ET and delta theta. Hold on a minute. Easier might be, maybe we can go through this. One moment. So this is basically the delta ET divided by delta T as time delta T goes to here. So that's basically dET dt. And I'm going to change this format such as d theta ds, ds dt. S is the distance it travels, that distance s. Okay. Now this is the position or distance divided by time would be gives you a velocity here. And that guy representing the curvature, which is 1 over r. And this is what we wanted to find that out. Okay, so d et divided by dt. So that's what we want to know. Okay, now but look at it over here. So delta et, and I'm gonna reduce the delta theta very small, and eventually this arrow will be going into the what is it? In the direction of normal directions. So this guy is basically, it's gonna be a en. Okay. So looking over here, so I'm gonna rewrite this guy here. The acceleration will be v dot et plus v dot and the e and 1 over r times velocity. So if I were to revisit that, the acceleration is going to be v dot et plus v squared divided by r en directions. So what this means is, if the particle is moving in this direction with a velocity or the speed of v, then the acceleration has 2 components. One of them is changing in the speed with respect to time, and I have another component in that direction. That would be this guy. So this would be the, okay, so this direction is E theta, and that direction is En. So tangential direction and the normal direction. So in the tangential direction, we only have a velocity component in the tangential direction. I mean, as I explained that the the velocity or particle going through or moving along the curve, the velocity will be always tangent to the path. Okay, so the velocity is a speed times et. So velocity in the tangential direction. There is nothing in the normal directions. But however, we will have one component in the, for the accelerations. When we look at the accelerations, we have two components. One of them is changing in speed with respect to time along the tangential directions. And in the normal direction, we have a acceleration terms, which is the velocity or speed squared divided by r. R is a radius of curvature. So which means that this goes in this direction, and imaginary that you can fit some kind of a circle, and that radius is the curvature, the radius of curvature. If this guy is a flattened, then your R is large. If this is a very, this guy turns very, sharp corner, then your radius curvature is smaller. Okay, so that's what it is. And another coordinates that we can use is a radial and the transverse components, coordinate systems. So we're talking about the same particle. It travels T1 and T2. Same thing, okay? In this case, I can define this as R1 position at 1, position 2, or position at time 1, position at time 2. In this case, up to now, we've been defining it along the curve in the normal directions. But this time, it is defined.
Thank you, Professor.
Yeah. Hello? At this time, it is defined to be R directions, and its normal is E theta. Okay, so this is different than a tangential. Okay, and this is known as a radial. Give me a couple more seconds. I know it went over. And the transverse coordinate systems. So radial and the transverse coordinate systems. So in here, the radial would be, look at the following through the radius. That's the ER directions, and perpendicular to that is E theta. And if this guy is come in here, your ER is in this direction, E theta is 90 degrees to that. And so in this case, the position is defined to be R, ER. So velocity is taking the dr dt, and you do exactly the same thing. You will find out R, E, R, R theta dot E theta. And acceleration is you take the dv dt, and it becomes a R double dot minus R theta dot square ER plus R double dot times 2 times R dot and theta dot E theta dot. So it will have two components in the acceleration components, and the two components in the R and theta direction for the velocities. So this kinematics equation can be written as a radial and transverse component. Okay, so next time we're going to take a look at some relative motions, and so I think we can be able to close the chapter 1 probably next meeting. So if you have a chance, go through the problems at the back of the chapters and start working it. Okay, and that will probably be very beneficial. All right, more you do it, then that's better for you. All right, do you have any other questions for me? Okay.
Thank you, Professor.
Thank you, Professor.
Okay, good night, everyone.
Thank
Good
you.
night, Professor.
Thanks, Professor.
Professor?
Dr.
Yeah,
Kim,
I'm here.
yeah, I think I sent you a message.
Remind me again. The examinations are open book and open notes. So it's better to have some kind of a reference books. And having I don't know how much expensive that is, but it's probably very expensive. It's better to have some kind of a book.
Professor?
Books that you can rely on. Hold on. The quizzes are open everything. Okay, so that's not a problem. Oh, yeah, go ahead and ask me.
Yeah, so my question is, will you pull out questions from textbook for quizzes and exams?
Well, I can't say that, but it will be similar to, the questions that is
Okay.
shown in the other, at the end of the, But I cannot really give you one-to-one correspondence because people can search some solutions over the internet. So it's very difficult to control. The dean knows it, school knows it, everyone knows it. And also I have a report that some of you get together and you can get some kind of test done within about, searching everything within about 25 minutes, and the other 25 minutes, maybe you can probably copy it down. That kind of action is not preferred, but I can only control so much unless we're having a face-to-face, hybrid classes where you need to show up in one of these days, in school, then you do it. And that's going to be a purely open book examinations. But I give, formally, I give these type of questions. My tests are given as a closed book and closed notes so that I can give a very simple question. But nowadays, if I give a very simple ones, then everyone get their solutions from some